Hello, everyone, and thank you for joining today's Code Long. My name is Reese, and I'll be your moderator today. We're going to kick off the session in a couple of minutes. We're just waiting so everyone has a chance to join. In the meanwhile, though, we'd love to hear from you. So let us know where you're joining from using the chat or the comments, depending on what platform you're watching on. And yeah, tell us something that you'd like to get out of the session today. We are going to be using DataCamp Workspace today for the Code Long. So if you don't have an account already, then make sure you've got one. Make sure you get signed up. I'll be sending a link through so that you can go along with us on DataCamp Workspace. You won't need a paid account. You can do this all on a free account. But yeah, keep your eyes peeled for that link as well. Shortly as well, I'm going to be sending through a link so you can register for the event. Everyone that registers for the event will get sent the recording as well as the resources as well. You can keep an eye out for the link in the chat, but you can also head over to datacamp.com/webinars as well, and you should be able to sign up there. Brilliant. I think that's everything from me for the moment. So I will be back to repeat these messages for any new joiners shortly. But until then, enjoy the background music. Hello, everyone, and thank you for joining today's Code Long. My name is Reese, and I'll be your moderator today. We're going to kick off today's session in about a minute or so. We're just waiting so everyone has a chance to join. In the meanwhile, though, we'd love to hear from you. So let us know where you're joining from using the chat or the comments, depending on what platform you're watching on. And yeah, tell us something that you'd like to get out of today's webinar. If you have any questions at any point throughout the session, technical or theory, then please let us know using the chat as well, and we'll be saving them for the Q&A at the end. If you haven't registered for the event already, then please make sure that you do that. Head over to datacamp.com/webinars, or you can find the link that I've sent in the chat. I'll be sending it again shortly. And yeah, get registered, and we'll send you the recording as well as any other resources as well. Brilliant. We are going to be using DataCamp Workspace today. So if you don't have an account already, then please sign up for one. You'll only need a free one to code along with us today. And yeah, you can keep your eyes peeled. We'll be putting a QR code on screen as well as a link in the chat so you can code along with us shortly. Brilliant. I think that's everything from me. So now I'll hand you over to your host for today's session, Richie. Richie, please take it away.
Hi there, data scamps and data champs. This is Richie. Now, when you think of data analysis, the data type that first comes to mind is usually numbers. But advances in deep learning and database technology mean that images and videos are now fair game for analyzing. So I might go so far as saying that important computer vision tasks like image detection, image classification, and image recognition are well on their way to becoming mainstream activities for data scientists. So today we're going to do some image recognition on a very famous data set, Microsoft's Common Objects in Context. And our guest is Louise Remies, a co-founder and the CTO at ApertureDB, the maker of the image database ApertureDB. Louise leads the design and development of ApertureDB, and he previously worked as a research scientist at the Software and Systems Research Group at Intel Labs. Now, for those of you who were here 2 weeks ago, ApertureDB might sound familiar. So we had a great webinar on computer vision in business. So Reese can post a link to the recording in the chat. And Louise's colleague and co-founder Vishaka joined a panel to talk about different use cases of computer vision. So please do check out the recording when you get a chance. And I believe Vishaka is watching us on LinkedIn. So please do say hi to her in the chat. Now, with that, over to you, Louise.
All right, thank you. Yeah, let's get started. Today we're going to be covering, we're going to be running a code along session where we're going to learn how to simplify the image analytics using ApertureDB and Python. We're going to be using PyTorch. And the idea is going to be to explore a large data set with a lot of rich metadata and use that for doing analysis on how well some of the models that we're building are doing. So let's jump right into it. And the first thing that we're going to be doing is setting up all the network and all the machinery so that we can use some pre-trained models to run object detection over a set of images. So the original name of the session was simplifying image recognition. We started working on image recognition, but then we realized that a much more interesting and novel use case would be just running object detection. This is detecting all the different objects that are on a large image. So that's part of image analytics in general. So we're just going to go for that, which is a much more fun activity to do. So in this code session, what we're going to be doing is running 3 different pre-trained models and run object detection over those over certain images. And we're going to be using Python and PyTorch for retrieving and running the models. We're going to be using the COCO dataset, as Richie mentioned. Here's a link with more information about the COCO dataset. You can run these notebooks later on. They will always be accessible. And we're going to be retrieving the data from the COCO dataset from ApertureDB, rather than giving a copy of the dataset to each person participating here. We're all going to be using a single copy of the dataset, and we're going to be retrieving that data from ApertureDB. At the end of the code along session, basically you will learn 3 main things. One is going to be learn how to run different object detection models using PyTorch and the pre-trained models that they offer. The other thing that we're going to be learning is how to create and retrieve data sets using ApertureDB. And not only at a data set level, but we'll be able to create and manage different data sets as we need them. And finally, we're going to learn how to evaluate the performance of a model using what is the values on their bounding boxes. All the detections that we do on the image, we're going to compare them to a ground truth. Let's start it by first setting up and running these 3 pre-trained models that we're going to be using today. So the 3 models are one that is called ResNet 50. Is actually faster RCNN with the ResNet 50 backbone. This is the most accurate model that we have, but it's slower, as we will see. We'll also be using faster RCNN with MobileNet v3 backbone, which is much faster, but is less accurate. It's less accurate for some of the labels and not for the others. That's part of the evaluation that we'll be doing. And finally, we're going to be using RetinaNet, which is a good balance between speed and accuracy. Even though it's unless we run on GPUs, the speed is in the order of the first option, the ResNet-based option.
Oh, sorry to interrupt. Can you just increase the text size a little bit? I'm getting old and my eyesight's failing.
Absolutely. Is that better?
Yeah, maybe one more.
One more. Let's do it.
Thank you.
Awesome. All right, good. The first thing we're going to be doing is making sure that we have all the dependencies up and running. So we're going to be running this in the background. For this first part of the session, which is just the first notebook, we don't really need ApertureDB. We're just going to be using PyTorch and OpenCV, but ApertureDB installs all the dependencies. So that's why I'm running this. And once that installation is done, we should be good to go. So the first thing we're going to be doing is running an object detector. So we created a class for your convenience here so that you can analyze and use it later for your own purposes. And I'm going to walk you through a little bit of how it works. But we're just going to very briefly cover it because essentially what we're using are pre-trained models. And we're going to be using OpenCV and TIL to just display the images and run the different models over the images. So as a starting point, we're going to read an image from file. We have a couple of images here just for testing. So we have this image of a tennis player, and we have this image of a pizza on a table. And we're going to be running some inference just to get started over those images. So the first thing we need to do is just read the image from file in this case, and we need to do some color adjustment. This is just OpenCV machinery and the way that the network is configured. And then these are the three networks that we talk about that we're going to be using. These are the different choices that we'll have for running the these are the three models that we're going to be running. And the first thing that we're going to create is this bounding box detector. And this is part of this infer.py file that has this class. And I'm just going to very briefly walk you through. It has a very basic constructor. And here we specify the models that we're going to be using. And we're going to be using PyTorch. So what we need is these packages, which already come with these models already pre-trained. And we can optionally use GPU here if it is present. And this is all you really need to set up the model. So you see how simple it is. You just use what, because we're using PyTorch for this, and they already provide all these pre-trained models, we can just instantiate the class that is going to be running the model and the detection with just very few lines of code. So that's what we're going to be using, and that's pretty much what happens when we create this detector here. So on our first step, we're going to just take this image of the tennis player, create the detector, and run the inference function, which is going to run the detection and detect all the different objects that are present on that image. So let's go ahead and just run that. And as you can see, we have this image of this tennis player here, and there are only two detections with their confidence. So we have a person and a tennis racket. So far, so good. We are trying with RetinaNet, which is supposed to be the model that has a good balance between accuracy and speed. Let's just, for the sake of the example, change this network and let's run something else. Let's see if there is any difference. It doesn't look like there is much difference. Maybe it looks like the confidence of a person is higher in this case. But yeah, this is just one image. Let's try with another image here. Let's try with a pizza image and see what we get. Let's try again with RetinaNet. And let's see what we get. All right, with RetinaNet, we get a label for pizza, we get a label for dining table, and we get also a detection for a fork. You can see that the confidence are, especially the confidence on the pizza detection is not that high. But that's part of the nature of these different networks. And the important thing that we're going to be doing today is doing some evaluation of all these different models. So that we can iterate, and then later on, this is part of a larger pipeline where we train a new model, we test how well it's doing, and then we do this iteration process again. So so far so good. We have the model up and running, and now what we can do is compare the performance of the three models. We could do something very quick. Let me just to show you what I'm gonna do is run all the different detections. And let's use the image of the tennis player first. So I'm going to just run this cell again. And now I'm going to run the three detectors over that same image. Let's see what we get. So the ResNet model took 1.3 seconds. The MobileNet took 0.08. It is much faster, and then the RetinaNet took about the same order of magnitude, the same order of the same amount as ResNet, pretty much. So let's actually show the different images to see whether or not we are getting the exact same labels. So with ResNet, we're getting both the person and the tennis racket. With MobileNet, same. And with RetinaNet, same. So far, it looks like, at least for this image, both of the networks are giving us a really good detection. Let's try with a pizza image and see what happens. So we're going to switch this to the pizza image. And we are going to compare the performance of the three. Let's see what we get. All right. In this case, we get for ResNet, look that the pizza is not detected, or at least it's not detected with a confidence of at least 50%, so that we consider it a good detection. And for the case of ResNet, we only have a dining table and a fork. And for the case of MobileNet, we only get, oops, where did it go? Here. In the case of MobileNet, we also only get the dining table and the fork. But in the case of RetinaNet, the pizza was detected with 56% confidence. So we can already start seeing how, depending on the image, depending on the content of the image, depending on the lighting, depending on a lot of factors, some of the models will work better than others, right? And in some images, the models will perform the same, but in some other images, the models will perform completely different. And that is the analysis that we want to do. So just to get an idea, here, what I'm going to do here is just run infer on a loop on a number of images. Remember that we're reading the images from the file system here. It's just the image that is right here, present here. And the image is loaded in memory. And because we are training at certain speed right now, we are doing somewhere between 10 and 13 images per second. And this is an interesting piece of information to remember, because later what we're going to be doing is retrieving the images in real time from ApertureDB, and we're going to see how well we're doing in terms of the images per second. And we're going to see that there is not much difference, and I'm going to explain why. But for now, keep in mind that we have around these numbers. Of course, if we change the network for something that for a network that takes more time to run the inference, the number of images per second will drop, because we are pretty much bottlenecked by the inference pipeline. In this case, for the slower networks, we're doing at about 1 image per second, but on the fast network, we're doing 10 to 13 images per second. And these are numbers that are specific to the Jupyter Notebook and this environment, which is testing environment. In real life, you would deploy these, on a cluster on machines with GPUs, and it's going to be batch processing. You're going to do a lot of batching and prefetching, so you can get much higher speeds. But just for the sake of this experiment, we're taking the numbers that we're getting when we're doing the operations here. So, okay, you get the idea here. So far, so good. And so far, what we have is this detector class that using PyTorch implements, runs the different pre-trained models. These are again, the 3 pre-trained models that we're going to be using. Now, we have an idea that some of the models work better than others in certain images for certain labels, and we want to do a more larger scale evaluation to see how well these models are performing on a much richer data set, right? And with that, we're going to jump into the second part, which is this notebook 2, where we're going to be using ApertureDB to retrieve images from COCO dataset directly and running the inference and the object detection over the images, and computing a metric of how well they are when compared to ground truth. So you can go here to this link where you're going to be able to log into ApertureDB. In your case, you can use the credentials that are provided a little bit below on task 1. The user is researcher, and the password is this thing that you can copy paste. So you should be able to log in by coming here, researcher. And you will be able to see this thing that I'm seeing right here. I'm going to be using this one that has a little bit more permissions, because I'll be running a few things. So here what we have is the ApertureDB web UI that show us all the data that it's already pre-populated on the database. So we ingested the COCO dataset here. So we have the full COCO dataset, which is composed of bounding boxes, polygons, images, feature vectors that we added, and a few other things that we have been adding when trying this object detection model. ApertureDB also offers a way to very quickly search and look at the images. So we're going to be running a really quick query here, where you can see these images that we were playing with, the image of the tennis player with ground truth bounding boxes. These are the bounding boxes that are that they were generated by a person who actually did labeling. So they are high quality. We're considering these bounding boxes as ground truth. And we're going to be retrieving the values of these bounding boxes and compare them to what we're getting out of those different 3 models. We also have the image of a pizza here, where we have the ground truth bounding box for the pizza detection, the fork, and the dining table as well. What we're going to be doing is essentially retrieving this information and retrieving the information associated to pretty much all of the images in the data set, because we have the ground truth bounding boxes for all of them. And we're going to be comparing them to whatever we're getting from those models that we're going to be running. All right, so let's get started. This is kind of like an overview of the data that it's there. And our goal is going to be to evaluate and improve an object detection model. So this is a very common use case. You need to build a model because that model needs to run inference and make predictions, either about what's going to be the next movie that a person is going to want to watch, what is going to be the product that is likely for a person to buy if they bought certain product, or we're going to be, all of this inference that runs, we need to do evaluation of how well they're doing. In the case of object detection with bounding boxes, and because we have ground truth on the database, we can just compare whatever we're getting on the detection against what's on the database and come up with a metric to say whether or not they are doing well. So for example, we're going to go over these steps. Essentially, we're going to generate a data set using ApertureDB and PyTorch. We're going to run object detection over the images on the data set. This kind of like the second step here. The object detection is going to generate a set of bounding boxes that are going to be the infer bounding boxes, the detections. We're going to send those back to ApertureDB so that we store them there. And then we're going to do, we're going to run compute the performance for each image. So for each image, we're going to see how well the model did for that image based on the detections. We're going to compute a global performance for a specific model, and we're going to store that in ApertureDB. And the idea is that in this workflow, we are just going to improve the model that involves training. This is a step that we're not going to cover today because it involves training, and that takes a lot of time. And the process is essentially running over these steps and repeat and doing iterations over until we get to the performance of a model that we're happy with. So we're going to be working on all these different steps. The first step that we're going to be covering is the creation of a PyTorch dataset. And the way that we're going to create this PyTorch dataset that we're going to be using is through ApertureDB. So we are going to create a dataset object that is going to be fetching the images from ApertureDB as they are needed. Let's go right into it. So the first step is to create a connection to the ApertureDB instance. So the process is pretty much the same what you just did if you were following and if you had a chance to go to the web UI. It's doing that logging, but we also have a Python module for ApertureDB that allows you to create connections and run queries against ApertureDB. So that's going to be the first thing that we're going to be running. And the way that that works is that we just need to import the connector, and we're going to be importing some other things that we're going to be using later, like a PyTorch dataset and ways to display images. And we're going to connect to the DB, right? Very straightforward. We just specify a host and a user and a password. So let's run this. Everything went well. And the first thing that we're going to be running is, the first thing we're going to be doing to test the connection is running a very simple query. Now, ApertureDB has a query language that is specialized to deal with visual objects as first-class citizens. So we provide functionality to retrieve images, to store bounding boxes, to retrieve bounding boxes, to store feature vectors, or embeddings and run nearest neighbor computation. Our functionality is, we have a lot of functionality. You can visit our documentation website where you will find more information about the query language and all the different options that we have. For example, for doing image and and image operations. And we also have a YouTube tutorial video of 1 hour that will cover all the basics of the ApertureDB API. But for this code along session, I'm just going to show you how some of the queries work, and we're going to be running them. And you can investigate a little bit more later about exactly the specifics of these queries. The most basic query is just get status. So we're just going to be running a query that is going to retrieve whether or not we can connect and everything is fine. So let's run this. So it's very quick. That's why you will see. Let me clean the outputs. And we run that. And the query is very quick because it's just a status query. And we're running version 19 of ApertureDB, which is exactly the same as we are seeing on our status page here. So far, so good. We were able to connect to ApertureDB, and we should be ready to go. The second part that we're going to be working on is retrieving images from ApertureDB, because we need to learn how to retrieve an image and maybe learn how to retrieve the bounding boxes associated with the image so that we can create a data set. And we can use that data set to run the inference pipeline. So as I was mentioning before, this is a very short query that will allow us to retrieve an image from ApertureDB. So in this case, what we're going to be doing is running a find image, and we're going to constrain that based on the ID, right? In this case, I know that this ID corresponds to that image of the tennis player. I can come here and actually show you, because if I open this image, you will see that one of the properties associated with the image is this ID, which is the one that we're going to be using for filtering the image. So what this query is doing is just retrieving that one image that has that particular ID. And we just go ahead and let's just go ahead and run this. And as you can see, we get a response, and then we are displaying the actual image. This is the image that we're retrieving from ApertureDB. And we're getting this as a response, which is also, same as a query, it's a piece of JSON. Let's make it a little bit more interesting, and let's retrieve all the metadata properties associated with that image. We can do that with all properties equals true. So if we run that, what we're going to get is all the metadata information associated with that particular image. So this is the same that we are seeing on the web UI, really. And that's it. This is how easy it is to retrieve an image from ApertureDB. And from then on, everything that we do is just going to be variations of these queries. We're going to running queries that are a little bit more complicated and more rich, because we're going to be filtering images by their content based on the ground truth labels that we have. And we can create a data set out of that. So let's go ahead and do it. As for the next thing, we mentioned that whenever you, so we have the images and we have some ground truth bounding boxes associated with the images, right? So let's retrieve in a programmatic way all of those bounding boxes associated with image. So in that case, we're going to be running a query that is slightly different. This query is going to be running the same find image as before. We are declaring a reference that we're going to be using later. Again, this is internals of the API. But we are doing the same thing, just retrieving this specific image. And in this particular case, we're also retrieving all the bounding boxes associated with the image. So if we run this query, you will see that we are getting the bounding boxes, and we are getting all the properties associated with the bounding boxes, including the label, which is person. So we have person and tennis rackets as label. And each bounding box also has a source. The source in this case is ground truth, because that's the only information that we have for those images on the DB. And we also have I think we have a confidence somewhere. No, the confidence. All right, the confidence. We're gonna, whenever we whenever we run the detection, we're gonna get confidence for both for those images. So far, so good. What we have done so far is being able to retrieve these images from ApertureDB that are running on this COCO, on this URL that we shared. In this particular case, that database only stores the COCO dataset, but you can store as many datasets as you want on an ApertureDB instance. The next step is going to be to run a query and generate a PyTorch dataset so that we can use that PyTorch dataset either for running inference or in the future for running training. It is the same object. So what we're going to be doing here is doing all the imports for PyTorch and everything that we need. And we're going to be using the PyTorch dataset class. This is just a wrapper class that will generate a PyTorch dataset, and it's available to use in PyTorch very easily. So in this case, what we're going to be doing is creating a dataset out of a specific set of images. Each image on the COCO dataset has different properties, and one of the properties is the license. The license is just, corresponds to one of the specific Creative Commons licenses. It's just an integer value, but what we're going to be doing is retrieving all the image that in the case of the COCO dataset, all the images that have a license are images that are that have the corresponding bounding boxes. So we're going to be filtering based on whether or not the images have that particular property. So in this case, the query that we're going to be running to generate a dataset is going to be running a constraint based on the license value. Again, this is arbitrary, and later on we're going to be creating other datasets based on other things. We're going to limit to 100 just for to 1,000 just for demonstration purposes, and I'm going to and here we're not really going to be running the query. We're just going to be giving this query to the PyTorch dataset object on ApertureDB. And this is going to generate a dataset object. Now, the dataset object is something that then we can give to a data loader in PyTorch. This is terminology that is specific to Python. To PyTorch. But what data loaders allows you to do is to specify a data source, and they provide multi-processing and prefetching as part of this class, so that when you are running inference or running training using a model, as you're passing a set of images through the model, you in the background are retrieving the next batch of images that you're going to be passing through the model. And usually, because the bottleneck is on running the inference or running, crunching the numbers, doing all those, matrix multiplications when you're running the network, usually the bottleneck is on that computing side. So we have plenty of time to go to the file system, to memory, or even over the network to retrieve the next batch that is coming. And this is why we have this abstraction provided, because it's very useful to be able to express everything as a PyTorch dataset and then use it for running training or inference. As you can see, that the amount of code that you need for that is very little. This is all included in our Python packages, and all you need to specify is a query like this. And what you're going to get at the end of that is a PyTorch dataset. And as the images are needed and are requested, the data loader will take care of doing the prefetching and have all the images ready when you need them. So let's just run this here. As you can see, it's very quick. Why? Because all we're doing is running a metadata operation on the database, and we're not retrieving any images at this point. The images will be retrieved when they are needed, when there is as we start accessing the data set, and they're going to be prefetched. So we're not going to notice that the images are coming over the network. Just for demonstration purposes, I can, in reality, if we just comment this out and we rerun the query, you will see that the actual data set is 100,000 images, 123,000 images, right? So this is the total number of images. And the data set is already created and ready for us to use, even though it has 100,000 images. And again, the reason why it works so fast is because all we do when we create a data set is a metadata operation. And as the images are needed, they're going to be fetched from ApertureDB. So it's very straightforward to start using. You don't need to download any data sets. You don't need to download labels and manage, S3 objects and CSV files with metadata. Everything is stored in ApertureDB and ready for you to use. So we're done here. Let's put the limit back, just for the sake of the demo. And now that we know how to retrieve and create a data set from ApertureDB and access the images and the bounding boxes, and now that we also have a detector, we have 3 different variations of a detector based on these 3 different pre-trained networks, we can start testing. We can start testing how well this is performing. So now, kind of like the sky's the limit. So the first step was to, this is the pipeline that we're going to go over. The first step was to create a PyTorch data set, which it's done. We're going to be doing some variations if we have time at the end. The next step is running the detection. We have everything in place to run the detection. We need what we need to do is make sure that we ingest the bounding boxes into ApertureDB, right? So we have this step clear. We just need to build the machinery to run the ingestion of ApertureDB. As you can see here, we only have the ground truth bounding boxes, right? This is the only set of bounding boxes that we have for that image. But we know how to run the detector over the images. So what we're going to be doing now is I'm going to set up a detector, the mobile net detector. And I'm going to use the data loader. This is the images being retrieved from ApertureDB as they are needed. And I'm going to just run an example to see how many images we can process. We can process just to get an idea. And as you can see, we are between 10 and 13 images per second, which is the same that we were seeing when we were running the detection on a local image, right? And this is kind of like the most interesting thing. And because we are using PyTorch and the data loaders that will take care of doing the prefetching in different processes, by the time that we need to pass the image through the network, the image is already there, even though it was retrieved from the system, and even though here it's been retrieving over the internet. So you see the potential here. You no longer have to keep your own copy of the data set. You can have the data set on a shared database instance, and all of the people in your team can be interacting and using the same data set at the same time and retrieving the images as they're needed. So again, the caveat here, these numbers are not very, scientific, but this is just to show a point. But in reality, again, you'll be running at testing stage, and when you are doing, you're trying to learn what's going on, you're going to be using a Jupyter notebook, and you're going to be using all of these things, and you will notice no difference if you're retrieving the images from the network. And once you're done and you feel confident about the model, you will end up deploying this on a cluster that has GPUs, and it's going to be running this much faster. At the same time, the database is able to respond to, hundreds of thousands of queries per second. So even if you have a more intensive workload, you will be able to prefetch and retrieve those images at the speed that they're needed. Because again, the bottleneck is on the processing, on the computing side. So you have plenty of time to go and retrieve data even from the network. Okay, so far so good. So we run over the data set here using the data loader. And the other thing that we can do is just, we have this data set. So every time that we try to access an image on the data set, that image is going to be fetched from ApertureDB. So let's go ahead and run this here. This is just showing the image corresponding to that, showing the 7th image to the data set, which happens to be an image that you'll be familiar with, which is our tennis player, right? And let's say we just want to access the 8th element instead, which is going to be another image familiar to you, which is going to be the pizza. And we're showing both the pizza and the pizza with the detections of MobileNet here, right? So now what we have to do, so we have a data set, we're retrieving the images from ApertureDB. Let's go back to our map here. So we are ready to run inference over a large number of images over the entire data set and push the images into ApertureDB. In order to do that, that is step 3. We're going to compute the detection for images on the data set and push all those detections into ApertureDB. So this is done by this file. This file, we're leaving this file here for you to use later. But you don't have the right permissions to write stuff into ApertureDB. That's why I'm going to be running this on a separate thing. But here you can find all the logic that is needed. And I guess the most important thing to look here is this. We're going to find an image. And for each detection on that image, we're going to create a bounding box. Right? We have this API that allows us to create bounding boxes and associate them to images. So pretty much what we're going to be running is a set of queries that look like this. Now I'm going to be running these queries in the background because I have write permissions on the database. And it's going to take a minute to run all those 1,000 images through the detector and back and insert the information back to ApertureDB. So let's go back here to our step 4 to step 3. So while step 3 completes, so right now we're running our detection model that we learned how to use. We're retrieving the images from Aperture, running the detection, and pushing those bounding boxes into ApertureDB. And we're going to be done into this stage. But now we have to compare the bounding boxes. We have to learn whether or not those bounding boxes that we're getting as a result of the detection are good or not, right? And that is part of the, this overall pipeline. We always want to be improving our models so that their detections are better. So we need to come up with a metric on how well those detections are doing. And for the sake of the code along session, what we're going to be doing is generating a metric based on something that is very commonly used, which is the intersection over union. So the intersection over union, here you have a very good example. Intersection over union, so you have the ground truth bounding box, which is the green one, and the predicted bounding box, which is the red one. This is an example. And the intersection over union is computed in this way: is the overlap area of the bounding boxes divided by the area of the union of the bounding boxes. So if the bounding boxes are exactly the same, the intersection over union is going to be 1. And if the bounding boxes do not overlap at all, the intersection over union is going to be 0. And if there is some overlap, that will generate a value between 0 and 1. And that is usually what it's commonly used for establishing whether or not an infer bounding box, infer detection, is good when compared to ground truth. So in order to do, let's wait a little. So right now we have, let's see what's going on. We ingested the new bounding boxes. And if we come here, we'll probably see, yeah, do you see that now we have a few other bounding boxes already there? That is the result of the detection. So we run it for 1,000 images. It took less than a minute in this environment. We can, again, go much faster if we do this on a deployment on a cluster. But right now we have the new detections of the bounding boxes, and we're ready to compare them. So we prepare a function for you, which is called compare bounding boxes, and it's based on a functionality in ApertureDB called intersection over union. Let me show you very quickly how that works. On ApertureDB, you can run custom queries. First of all, let's check the bounding boxes that are present on the system. So we have 800,000 bounding boxes for ground truth, and we just have a few of the bounding boxes for MobileNet. This is because we just processed 1,000 images, right? We can get all of them if we want. But we're good to go. We're good to go. We have those bounding boxes ready. The next thing that I wanted to show you is how you can do intersection over union and what that means. So what we're going to be doing here is finding an image. We're going to constrain by the unique ID of an image. In this case, I think this is the tennis player. And then we're going to be finding the bounding boxes that are ground truth. And we're going to find the bounding boxes that are MobileNet, everything associated with the image. All of this is part of the same query. And then we're going to run the region intersection over union operation on ApertureDB, which is supported natively. That means that for every image, we can run a query that looks like this, where we compare the ground truth against MobileNet or pretty much any other network. that we evaluate, and we're gonna get a metric on how well those bounding boxes are. So after running the query, I get the result. So the result shows me the all the bounding boxes, and as you can see here, for ground truth we have a person and a racket, and then for MobileNet we also have a person and a racket, right? But when we compute the intersection over union, this is what we get, right? And the highest value here corresponds to the maximum intersection over union, which we can assume is the same bounding box that has been predicted. But you see that it is not one, it's 0.87 and 0.67, right? They're not perfect. That is what we can do with. But just by running one query in ApertureDB, after we have ingested all the metadata, we can get a value for the intersection over union and know exactly how well our detector is performing. So what we added here on the notebook is just a small function. The function is on this infer.py file that we shared with you. And what this compare bounding box is doing is pretty much running the same query that we just showed you. And what it's doing is iterating over all of the bounding boxes in the image and computing the average score, right? So let's see what that looks like. Let's go back here. And let's run this for the tennis image and from the pizza for the pizza image, and let's see what we get. So as you can see here are the bounding boxes that are detected. The person and the ground truth labeled person is the same as the predicted labeled person. And then the ground truth racket, tennis racket, and the prediction level tennis racket are the same. So we're going to average those, and that gives us a score of 0.77 just for this image, right? So the same, when we run the same for the pizza image, we see that we have 90% for fork. We have 84%, but we have a ground truth of pizza, and the prediction label is bowl. So this is a wrong detection, right? And then we have the other detection, which overlaps almost perfectly, which is the dining table, which is detected by both. But the score is much lower because this is a detection that was missed, even though it's 84% accuracy, but it's on the wrong label, right? So that's why the score, even though we're averaging all of these, we're not taking into account this value. Again, all of this is arbitrary, and it really depends on the use case, how you want to do this. But we get all the intersection over union from ApertureDB, so we can do pretty much whatever we need after that. And this is how we compare for one image. Now we can, what we're going to do is for MobileNet, we're going to create a new data set where we're going to find all the images that has a bound, that all the images that have bounding boxes with this source. We're going to create a data set for that. And then we, let's run that. So that gives us 958 images and not 1,000, because not all of the 1,000 images that we ran the detection on, not all of them had bounding boxes. Some of them didn't have any bounding boxes and any detections at all. And now what we're going to do here is a little bit of Python and threading so that we run things in parallel. We're going to be running, because here we're going to be running multiple requests into ApertureDB to retrieve those intersection over unions. And we're going to compute a global score for that model. So let's run that. Let's see what we get. And again, this is, pretty much 1,000 queries that are going to be translated, that are going to be sent to ApertureDB and give us a score, an overall score. So if we average the score of all the images of all the detections for MobileNet, we get 0.36, which is pretty low, right? Pretty low. So what I'm going to do is, in parallel, I'm going to be ingesting another set of bounding boxes that will hopefully be better. But right now, we have the global value for the MobileNet model. And we're ready to go to the final step, which is, so we're already here computing the performance model and storing that model into ApertureDB. How do we do that? We're gonna do something where we're going to find all the images that have a bounding box with that model. Here we get the images, and we're going to connect all of those images to a new entity that we're going to be adding. Let's call it object model detection code along, right? And we're going to store the model and the score, right? The internals of the query, again, I'm going to leave it for later, but we run this query. Oh, of course, we're not authorized to perform these actions. I need to run, I'm going to run this query somewhere else because I have write permissions. Give me one sec. And all right, so we run this query, and as you can see here, we have an object detection class, which essentially links to all the images that were used to compute the performance of that particular model. And I guess another thing that we can do is I have a query here that is going to run and find all the models that we have and all their respective score. So this is something that I pre-computed beforehand. We were getting 0.36 for MobileNet, but for RetinaNet, it was slightly higher, right? 0.46. Because the model, even though it's the model is lower, but it gives us a better performance in general, right? So the other thing that we're going to run here, we computed for MobileNet. Let's change that, and let's do it over RetinaNet, just for demonstration purposes. We have a few less images on the, sorry, when we run the query, we have a few less images. We have 921. It doesn't really matter. It could be hundreds of thousands, right? Because they are retrieved as they are needed. So it's really fast to compute. And the final part that we're going to be doing is computing that global score for that specific network, which based on what we computed beforehand, it should be around 0.4. Okay, good. That's what we get. And yeah, the cycle will be the same, right? After we compute the performance model, we store that on ApertureDB, and we store both information about the model and all the images that were used to compute the performance of that model. And we have our evaluation ready. We are ready to figure out what's going on, why the detection is not as good as we would want, run some training, inference, improve the model, and run this cycle again. And with ApertureDB, one thing that you can very easily do is, right now we're creating data sets based on or a particular value, but we can also create a data set of images that have only rackets, for example. And this is going to be the final example that I'm going to be showing you, where we can create a data set using images. Well, the example that I have here is I don't want all of the images, or I just want images of dogs and cats, and I can maybe generate a data set for that specifically, right? So what I'm going to do is finding all the bounding boxes that have a ground truth with dogs and cats and retrieve all the images. And here I'm limiting to 10. Just for demonstration purposes. But out of all of those images, we can get exactly those images that corresponds to either dogs and cats, and use these images specifically for either running training or for doing the evaluation of the model, right? And again, you don't need to hold this data set on your machine because the images can be prefetched as they are needed directly from the database. And with that, and slightly over time, I am going to stop here for any questions.
Thank you. That was magnificent. I have to say, whenever I see things like this, it does feel like I'm living in the future. I mean, that was like some pretty powerful stuff going on there. And yeah, pretty simple to do. Now, we have a ton of questions from the audience. Before we get to audience questions, I have one question for you. So I think one thing that really surprised me there was that the pizza was very hard to detect. Like, now in my mind, pizza is a very common object. It's got quite a distinctive sort of visual appearance. So can you tell me a bit more about what makes an object easy or difficult to detect?
It's hard to tell, especially on these models that are, CNNs, and they are not using any. We're using these models that are they have some years. They have been there for some time, so they're not the best models that are out there. Usually, what people do is take those models and use transfer learning from those models and retrain them for their specific use case. Let's say you need to run a detector for finding chairs and tables. So they will take this model and retrain it with more specific data sets to improve the performance. It depends on the lighting. It depends on the example set that at training time the network saw. So it depends on a lot of factors. What happens usually on this, and specifically in COCO and the models that are designed to train on COCO, is that COCO is a research type of data set. So it has labels that are all over the place. They have images that are coming from, these are images that some of them are coming from the YFCC data set, which are images that people upload. So the lighting is all different. There are a lot of different conditions. And the other thing is that we're running images that are quite large. So even small things, sometimes, I don't know if you remember, there was a ball detection. So that ball detection is actually a detection that happens over one of the pepperoni pieces. And this is because, the image is very large. So even a small set of pixels can be classified as something. It's very application dependent, but in this particular case, because it's a research data set, all of these effects happen.
Okay. All right. So actually, that leads nicely to an audience question. So I was asking why you're not using yellow. So as I understand, there's sort of 3 different classes of image models. You've got the regional convolutional neural nets that we're using today. YOLO is you only look once, and then the other one is single shot detection. So there's like 3 different classes. Can you talk a bit about like when you might prefer one over the other?
Okay, yeah.
Sorry, that's a difficult question, I guess.
Let me open these. So we try these different models in different applications, and we were not able to arrive at it works on certain use cases better than others. When you have a set of images that are the lighting conditions are very similar, and you just have changing of different objects, as it is the case on one of our customers, that they sell different products, right? And they sell a chair, they sell a table, a couch, right? And usually the way that those photos are taken is that they take the object to a place that has a right lighting, and everything is pretty much standard. You just need to run detection over of a reduced set of objects. The mobile light was really good, was good enough for what it's needed. And the decision, so it's hard to tell which one are better for different use cases. And that's why there is a need. That's why we went over, showing this entire pipeline, because the most common case is that you don't know, and you need to run different iterations, and you need to try different data sets until you arrive to something that it's within the metrics that you're expecting, because, everything is optimal given the right criteria. So if the model works for you after the evaluation that you do for your specific use case, that is what we should go with. Most of the decisions that we made, because we're more on the infrastructure side, is based on the trade-off between performance and between the accuracy and how fast they are. That is what we care the most about and what we know the most about. So that's why we mentioned this here. But yeah, I don't think I can give you a better answer than that on when to use one model or the other. It's very application specific.
Okay, so it's probably a case of try a few and see which one has the highest accuracy and see how fast each one is.
Yeah, and train again and transfer learning and train again and try different data sets until you get the metric that is good enough for your business use case.
All right, brilliant. And next question comes from Victor. So we're looking at individual images today. So can you just talk about how you go out transferring your image analysis to a video analysis? Is this a case of like analyzing one frame at a time, or is there something fancier you can do?
Good, yeah. So ApertureDB has full support for videos. So we have support for videos, feature vectors, a lot of different things. Everything that it's related with visual analytics, we have support for it. We could build a data set of videos. So in the case of videos, it really depends on the use case. Sometimes what you want is to run detection, the same detection that we run over maybe not all the frames, but most of the frames on the video to see whether or not there are some objects present in that video. There are some other things that you can do with that involves passing not just one frame, but a sequence of frames and doing activity recognition. You need a completely different model for that. It takes a lot of time to train. But all the things that we learned here on how we can retrieve that metadata information from Aperture and actually retrieve the videos or frames or even clips within the video, that support that we have for it, because these are all different variations that you would use for doing analytics. So we have one customer that is running, they need to do activity recognition. They need to recognize when a person is doing a particular activity, but they have very short videos. So what they train is on the full short videos that they retrieve from, that they will be retrieving from Aperture. And in this case, because they have short videos, they pass the entire videos through the neural net. But we have some other use cases where they have a larger video and they run a model to, here's another example. You can run a model every if you have a 30 frames per second video, maybe you can run every 30 frames, you run a detection to see if there is a person. And if there is a person on that specific frame, you create a clip of short duration and retrieve only that from ApertureDB to pass it through the network. So again, it also really depends on the use case, but the way in which you work through that, it's very similar to what we show here on images. You'll have these bounding boxes, these detections, and you're going to be filtering based on that.
Okay, so you can sort of take advantage of the fact that stuff from one frame to the next is probably going to be quite similar.
Right.
Yeah. All right. So easy question here from Rich. So how does one install and use PyTorch? So if you're using Workspace, PyTorch is already installed. You just need to do import torch. The trick is don't put the Py on there when you're typing it. So easy peasy. Slightly trickier question from Jane. So Jane says, how do you know the bounding boxes have the same object label?
That's a good question. So, and that's something that we had to spend a little bit of more time understanding what was happening, because at the beginning we were getting a very low overall performance on the model, and it was because of that. And that's why at some point we covered that the metric that we come up with for every image and for the global metric for the model is based on both the intersection over union operation and the fact that the labels of the predicted has to be the same as the ground truth, right? And that's why we need to run intersection over union of all the bounding boxes in the ground truth against all the bounding boxes that are predicted. And we compute the intersection over union. And for each case, we take the maximum and we compare whether or not the labels are the same. If the labels are not the same, we just say this detection is wrong, as it was the case on the pizza and the bowl thing. That was the pepperoni piece that was detected as a bowl. And we kind of like punish the score because the detection was not correct.
Okay, nice. So we're at time now. We're going to run a couple of minutes over because there are some very cool questions left to ask.
Absolutely.
For everyone who has to jump, before you go, I just want to say we've got another great webinar on Thursday with the CEO of DAGShub talking about MLOps. Please do go to datacamp.com/webinars. See you again on Thursday, hopefully. I have a related question about the bounding boxes. So we always use rectangular bounding boxes there. Is there a reason for that? Is it just because it's easiest? And would you ever want a different shape of bounding box?
Oh, yeah. So we're using bounding boxes just for demonstration purposes, but on ApertureDB, we have support for polygons as well. We actually have all the polygons stored for the COCO dataset. So you can, with the credentials and everything that you see there, you can actually go into ApertureDB and retrieve all those polygons corresponding to all the ground truth labels. We also have polygons there. You could detect, so another task which is different from, you can do object detection generating masks, which essentially will give you a polygon of the object. So at the pixel level, you mark the pixels that correspond to that particular object. And you can run the same operation. You can run intersection over union over those polygons to compute whether or not they are they're accurate. And it's kind of like the same process. We just use rectangular bounding boxes here because it is kind of like the most straightforward. But on ApertureDB, we have support for polygons. You can retrieve the polygons. You can compute intersection over union on polygons too. You just need a model that instead of giving you bounding boxes, it will also give you polygons that you can compare.
Okay, so it's kind of a property of the model and everything built into ApertureDB. All right, nice. Okay, we've had a few questions around performance. Can I do this in real time, things like that? So
Yes.
I'm just going to take this one from Yash. So Yash asks, can we use GPUs or TPUs to improve the performance?
Absolutely. So the way that you would, after you have experimented and you have a model that you like, or even if you deploy this pipeline that we build, let's say on a production environment, and this is something that it's always running and we're always testing and evaluating the model, that can be running on GPU. So all the every time that we run inference here, that is something that can be moved into a GPU and it can be run. If the GPU is present on the system with the code as it is right now, it will pick it up from there. That is on the client side where we're running the inference. On ApertureDB, we can also perform operations. We can also, like, we were retrieving the full images, but we can retrieve we can retrieve the image in half the size, and the resizing will happen on ApertureDB, so that you transfer less data, right? We also have for running all those resizing and all of those operations that we support in ApertureDB, we could potentially run them on GPUs on the server side. Right now, we're not doing it because most of the bottleneck happens when we're doing training on inference on the client side outside of ApertureDB. So all of these resize operations and cropping and the basic operations that we support run fast enough on the powerful CPUs that we have on the server side. But on the server side, that's where you can use GPUs. And on the client side, when you're running the inference, it totally makes sense to use GPUs. It's going to be much faster than what we showed today.
Excellent. Just sound like GPUs are going to be a big speed up there. All right. So very last questions. So this is another one from Alex, just saying, can you detect criminal activity on street threats and also keep privacy? So this is like quite an important sort of social issue. Is like it's sort of possible to detect people's faces and see what they're up to with security cameras, but some ethical issues there. Do you want to give us a quick overview?
Yeah, so that goes more into the application side of things, where we have less expertise. Most of our expertise is on the infrastructure side and making sure that the data is where it has to be at the moment that it has to be for processing. That question is more on the how would you go about implementing that. And I've seen both research work and some work in some airports where there are cameras looking at specific spots, and they are running this activity recognition over short clips of videos to detect whether or not there is, someone falls or there is a fight or things like that. I've seen those applications actually up and running in certain places. It's really hard to detect, certain types of activities, right? So it's been deployed in a narrow scope. But my guess is that if you want to go about implementing something like that, it will be a matter of training good detectors so that you can have a camera pointing somewhere and being able to recognize whether or not people are doing certain activities, like, having a classifier for seeing whether or not people are, fighting or running or falling or those kind of things. Now, exactly what is the best model to do that and where would you start off? I don't know. But the process, the infrastructure process, would be pretty much or very similar to what we saw today.
Okay. All right. So actually, for people who are interested in this, on the Data Frame podcast, we had a great episode. I was interviewing Joy Bolamwini. I think Reese is just posting a link in the chat. So if you are interested in some of the sort of the ethical issues around facial detection, facial recognition, then please do click through and check that out. All right. So with that, we are well over time. So thank you once again, Luis. That was amazing.
Thanks for the invitation.
Really, really fancy stuff. I hope everyone learned a lot. Thank you as well to Reese for moderating. Thank you to everyone who asked a question. Sorry we didn't get to all of them. Thank you to everyone who showed up today. I hope to see you again Thursday, and then next week I think we've got 3 or 4 sessions as well. So I will see you all again in future webinars. All right. Thank you.
Thank you.